Hello learners, welcome back to the course on deformation processing of materials. In the previous class, we had seen some parameters related to the extrusion process. And towards the end, we saw some special type of extrusion processes. Now let us begin today's class with the topic related to forces in extrusion process. Okay, so today we will see forces in extrusion. Forces in extrusion. Okay. So basically, during the extrusion, we have seen several times that the cross-sectional area gets reduced. Okay, so suppose A naught was my initial area and AF is the final area. And suppose this is the RAM, which is pushing this billet. Okay, so here the area was A naught and here the area becomes AF. Okay. So in this case, the force is given as if we multiply the stress by area, then it becomes the force value. And in this particular case of extrusion, we need to consider the reduction in cross section area. So true strain also gets multiplied here. Okay, so force will become stress into initial area into the true strain value. Okay. And basically, this is the minimum value of force which is required. So this will be minimum force required. We cannot go below this value. In that case, extrusion will not be possible. So this is sigma naught A naught, and this true strain can be written as ln of initial area by final area or final length by initial length, as we have seen. Okay, so this will be E naught over AF, or it can be written in terms of the extrusion ratio also. So this will be sigma naught A naught ln of R. We have seen this in previous lectures also, that this A naught by AF is nothing but the reduction ratio or the extrusion ratio. Okay. So this relation gives us the value of minimum force required. Here, let me put it in a box so that it becomes more clear. Okay, so here Fmin is nothing but the minimum force required for extrusion. Minimum force required for extrusion. Okay, and sigma naught is the flow stress. A naught is the initial cross-sectional area. Initial area, and this ET is nothing but the true strain. ET is true strain, or R is the extrusion ratio or reduction ratio. Extrusion ratio. But here what happens is that we have neglected the effect of friction and non-homogeneous deformation, etc. So we need to take them also into account. So for that particular case, the force which is calculated will be the actual force which will be required for extrusion. Okay, so the actual force will be similar in nature, means it will also have the similar kind of relationship with the area and true strain. Okay, so say it is F actual, and it will be nothing but a constant K times the initial area multiplied by ln of A naught by AF. Okay. This is similar relation. Only thing is the flow stress now has been replaced with some constant, which is known as the extrusion constant, which takes into account the effect of friction and non-homogeneous deformations, etc. Okay, so here K is known as the extrusion constant. Extrusion constant. Okay. And it has unit similar as that of stress or flow stress. Unit is same as sigma. Okay. And this accounts for uh, all all of the values like flow stress, friction, and non-homogeneous deformation. And it this K accounts for sigma naught, friction, and non-homogeneous deformation. Non-homogeneous deformation. Okay. So these were two relations giving us the value of force required for extrusion. Now, if we take the ratio of these two, we will get the efficiency of extrusion process. Okay. So efficiency of extrusion is given as, say, it is eta of extrusion is nothing but the ratio of minimum force required to the actual force required. And if we substitute the values from the above relations, what we get is this was sigma naught A naught ln of A naught by AF, and this was nothing but K into A naught ln of A naught by AF. These two terms get cancelled out. So we are left only with sigma naught over K. So this eta becomes sigma naught over. So this relation gives us the efficiency of extrusion process. Now let us see some numerical examples related to these expressions or utilizing these equations so that we can have a better understanding of these. So suppose the question is, suppose a brass billet is being extruded. Brass means it will be around 70% copper, 30% zinc. This will be the composition. This brass is being extruded, and we are given with the values of temperature, the extrusion constant, initial and final diameters, and finally we need to calculate the force required for extrusion process. Okay, so a brass billet is being extruded. Okay? A brass billet to be, let me write the composition of brass also. So this is 70 copper, 30 zinc. So is to be extruded, and we are given with some parameters like temperature, temperature T is 700 degrees Celsius. Okay, and the extrusion constant K is 250 MPa. Okay. We are given with the initial and final diameters also. So let us say circular workpiece is being extruded, something like this. So this is D naught, this is E naught, and this is DF. Okay. So we are given with the values of D naught and DF also. D naught is given to us as 100 mm and DF is nothing but 50 mm. Now we need to calculate the extrusion force required. Extrusion force. So let us see how we can calculate the values. So we have seen that the force value or actual force value is given as F actual was nothing but K times the initial area times ln of the ratios of initial area to final area. Okay. Or we can say that it was nothing but K times A naught into true strain. Okay. So we will be using this equation only, and here we know the value of K, we know the value of A naught since we know D naught. So basically we need to calculate the true strain and substitute all the values here. Okay, so the true strain will be nothing but ln of A naught by F naught, A naught by AF. Okay, so ln of A naught by AF, and this will be nothing but ln of pi d naught square by 4 whole divided by pi df square by 4, considering circular cross section. So this ultimately becomes ln of d naught by df square. Okay. And if we substitute the values, what we get is et is nothing but 2 times ln of this d naught is 100 and df is 50. So this approximately comes out to be 1.386. Okay. So this is the value of true strain. Now, if we substitute the values of K, A naught and true strain into equation 1, we will get the value of force. Therefore, F actual will be nothing but K is 250, A naught will be pi d naught square by 4, and this value we have calculated it as 1.386. Okay, so if we calculate it, it comes out to be uh, the force value. Let me substitute this. So it will be 250 into pi by 4. See here, the K value is given in megapascals, and megapascal is nothing but Newton per mm square. So in order to get the value of force in newtons, we simply need to put the value of area in mm square only. Okay, so I'm directly putting 100 square. If 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 I had put the value of K in pascals, then I in that case I would have to put the value of this area also in meter square. So here I'm directly putting as 100 square. Okay. And this was 1.386. And upon calculation, this value comes out to be 2.72 into 10 to power 6 Newton. Okay. So this is the value of force we needed to calculate this only. Okay. It can also be written as 2.72 mega Newton. Okay. So now let us see another example. Now again, we have a numerical where some data has been given to us and we need to calculate the average pressure there. Okay, so here we are given with the condition that direct extrusion is being done. Direct extrusion is being done. Okay. And we are given with the initial length, initial diameter of the workpiece, and also we are given with the extrusion ratio. Okay. So L naught is given as 100 mm. D naught has been given as 50 mm, and the extrusion ratio R, which is nothing but A naught over AF, it has been given as 4. And we are also given with the average flow stress. So average flow stress, which is nothing but sigma F bar. It is given to us as 300 megapascals. Okay. So now we need to calculate the average pressure. And calculate average pressure. And as we have seen earlier, uh, pressure will be nothing but will be a kind of stress only. But since it is being talked about or in case of extrusion, so we need to consider the parameters or reduction in cross section also due to the extrusion process. So to incorporate that, we need to consider the true strain also. Okay. So the average pressure will be nothing but product of this average flow stress and the true strain. Okay. Therefore, the average pressure will be average pressure will be nothing but the average flow stress into the true strain. Which will be nothing but, you can write it as P is nothing but sigma f bar into et. So we will be using this equation. Now we are given with sigma f bar and we only need to calculate et here. So the true strain et is nothing but ln of a naught by af, which will be nothing but ln of r. Okay. So if we put the values, this p becomes 300 into ln of r, which is nothing but 4 here. Okay. So upon calculation, we get the value of pressure as approximately 416 megapascals. So this gives us the average pressure in case of this extrusion process. Okay. So this was another example. Let us see one more. Okay. So again, we are given with an extrusion process. Here we are given with the values of initial and final diameter of the workpiece, the average flow stress, and here we need to find the minimum force required. Earlier we calculated the actual force. Now in this problem we will see the minimum force required. So we are given with d naught. D naught is given to us as 10 mm. df will be 8 mm here, and the flow stress here is, say it is average flow stress, so it is approximately 400 ampere. Okay. And we need to find the minimum force required. Calculate F. Okay. So let us see the solution. These are simple questions needing substitution and some manipulation of some values and then substitution into the standard equations. Okay. So here we know that the minimum force is given as sigma f bar a naught true strain. Okay. So again, in this case, our primary focus will be to calculate the true strain and then substitute into this equation. Okay. So true strain here is given as ln of a naught by af. Okay. And we know that this area can be written in terms of diameter, so we will get ln of d naught by df square, which this is square. Okay. This will become 2 times ln of d naught by df. Okay, so this true strain comes out to be 2 times ln of 10 by 8. Okay. So if we substitute this back into the equation of F minimum, this F min will be 400 into initial area is 5 by 4 d naught square. Again the same thing. 400 is in megapascal, means this sigma F is in megapascal. So I'll put the diameter directly in mm. Area will be mm square. So this is 10 square. Okay. And this will be 2 times ln of 10 by 8. Okay, so upon calculating the values, or means solving this equation, we will get F minimum is nothing but 1.402 into 10 to power 4 Newton. Okay. So this again gives us the value of minimum force required. So with this, we have now completed the process of extrusion, or the metal forming process known as extrusion. Okay. Let us quickly see one of the major defects which is observed in case of extrusion process. Okay, so basically what happens is, when about 2/3 of the billet has been extruded, what happens basically is, the surface which is in contact with the container starts to pass through the orifice and go into the extruded portion, and the portion which was in contact with the surface of container uh, generally gets oxidized, or uh, forms, there is formation of oxide layers over there. Okay. So what happens is that these oxides now get passed into the extruded product. So they are present in the form of defects in the extruded part, and if we cut the cross section and see this section of extruded portion, it appears like a annular ring over there. Okay, so this is a major defect which is observed in this extrusion process, and it is known as extrusion defect itself. Okay, so extrusion defect, extrusion defect. So what happens here is, when 2/3 of the billet has been extruded, after extrusion of 2/3 of the billet, the surface of billet which was in contact with the container the surface of billet in contact with container wall starts to move towards the center, starts to move towards the center. Okay, and since this contains several oxides, these oxides also start to flow into oxide stringers which are entrapped into the extruded product or extrusion part. As this surface contains oxides, these oxides gets these oxides get or are passed to the extrusion as oxide stringers. Okay. Oxide stringers, and this is known as extrusion defect. This is known as extrusion defect. And if we see the cross section of the extrusion, these defects appear as annular rings. If we see the transverse section of the extruded product or extrusion, these appear as annular rings. Annular rings. So it was one of the means it was the major defect which is observed in case of extrusion process. So with this, we have come to the end of this extrusion metal forming process also. So hope this would have given you a overall idea or overview of the extrusion process. So now let us begin the next metal forming process. Let us see the next one, and we will now discuss about the deep drawing process or cup drawing process, which is a kind of sheet metal forming process. Okay. So now let us begin. The deep drawing process. This is also known as cup drawing or simply drawing. So before we see what is meant by deep drawing, let us see some major distinctions between the bulk forming processes that we have seen earlier and what is the major difference between this deep drawing and the bulk forming process. Okay. So in case of bulk forming processes, we have seen that mainly compressive stresses were being used. But here we will see that majorly tensile stresses in the plane of metal sheet are used to form it into shapes like cup, etc. Okay. So uh, in bulk forming, mainly compressive stresses were being used. Mainly compressive stresses are used. But here, in case of deep drawing or sheet metal forming, in sheet metal forming, tensile stresses in the plane of sheet metal are applied. So tensile stresses in the plane of the sheet metal are applied to cause the deformation. Cause the deformation. Okay. So why is it so? because application of compressive stresses may result in buckling of these metal sheets. Okay. Compressive loading may lead to buckling and wrinkling. Buckling and wrinkling. So, in order to avoid this, uh, mainly tensile stresses are used. Yeah. Also, we should keep in mind during this sheet metal forming that there should not be much reduction in the thickness of sheet because it may ultimately lead to necking and cracking, so ultimately leading to failure. So this is another important point that in the sheet metal forming process, in sheet metal forming processes, the thickness reduction should be avoided as it may lead to necking and failure. Okay. Yes, it may lead to failure due to necking. So these were some important aspects or points to be kept in mind while performing the sheet metal forming operations. So now let us see what is meant by deep drawing and how this process is done or carried out. So deep drawing is basically a process of uh, forming cups, etc., out of metal sheets by application of loads through punches, and the sheets which are initial metal sheets which are used for forming the cups is known as blank here. So the punches are used to press the blanks into preformed dies which have the shape of final product. So ultimately those sheets or blanks take the shape of the die and get converted into desired shape or product. Okay, so deep drawing is basically a metal working process. Deep drawing is a forming process in which flat metal sheets, generally metal sheets are used, and this process is used for metal, so we frequently use the term metal, in which flat sheets are shaped shaped into cups. Okay. We should not say cups only because there may be several other shapes similar to cups, like there may be glasses also or tubs also. So shape similar to that of cup, okay, are shaped into tubs, shell, cups, etc. So let us see the schematic representation, how the blank is placed into the holder and what are the names of various components used in this process. Okay, so let us say initially there is a sheet. Okay, so it is a metal disc or sheet which we will be using as blank. So its initial diameter is denoted as diameter of blank or dB. So this is dB. So this blank is put into the uh, setup or the mechanism made for deep drawing, and it is pressed using punch. Okay, so let us see that arrangement also. So there will be some dies. There will be dies like this. There will be dies like this. And upon these dies, the blank will be put. Let me change the color of color here for better visibility. So let us. Okay, so let us say our blank is put on the die like this. We should not call it as put. It is basically placed there. Not only put, it is clamped with the help of holders. So say the blank has been kept like this. So it is folded at its place using hold down rings or blank holders. So suppose these are our blank holders. So they keep the blank in its position by pressing it down on the die. They are just to hold it. Okay. And there will be a punch. There will be a punch like this. Which will be pressed so that it pushes the blank into the die so that it takes the shape of that particular die. Okay, so we saw that this was the diameter of our blank, and the punch diameter is also of very prime importance. Okay, so say this is the diameter of our punch. It is denoted as TP. Okay. There is a relation between the blank diameter and punch diameter, which we will see in a while. Okay, so what happened to it? Suddenly went. Okay, so we are here. So we will see in a while what is the relation between the blank diameter and the punch diameter. So the height of this blank. The height of the blank is denoted by h. Say the initial height is h naught. We should not call it height, it is the thickness. H naught, thickness of initial thickness of the blank. And here load, say load P is being applied. Let me change the color. Okay, so this is load P. And these were the dies. So die, this was punch. This is hold down ring or blank holder. Blank holder or hold down ring. Hold down ring. Okay. This is our blank. It's a bit difficult to control it. So this is our blank. And this is the setup for deep drawing operation. So basically deep drawing is done using this kind of setup. Okay. So if we consider some parameters, then we will have to keep in view that the rate of the coefficient of strain hardening that should not increase much with the deformation in case of sheet metal forming. Okay. So in sheet metal forming, the N value should not increase with deformation and should not increase with deformation. Also, in case of rolling, extrusion, etc., in hot working condition, the recrystallized microstructure was being observed or being obtained in the product. But in case of this drawing operation, it is generally done as cold working. So that phenomena is not generally observed. Recrystallized microstructure is generally not seen here. Okay. Also, there is a contribution of roughness parameter if we see. So in case of that particularly belongs to ruling operation, that when the roughness parameter is low or during cold rolling the surface finish was being obtained as very good, and in case of hot rolling when roughness parameter is high, the surface finish is hampered. But that is not related to drawing, so let us move to the next parameter related to drawing operation. So in case of deep drawing, there is a parameter known as drawability. So drawability is basically the ratio of initial blank diameter to the diameter of final product, that is cup or tub, which is generally approximated by the diameter of punch, because the cup will have final diameter as equal to that of cup on the punch only. Okay, so the next parameter which we are seeing is drawability. solubility. So it is nothing but the ratio of initial blank diameter to the diameter of the cup. Okay. And also the diameter of cup is approximated equal to that of the punch. So we have seen that blank diameter is represented as dB and punch diameter is represented as dP. So the drawability will be dB over dP. So this gives us the relation between initial and final diameters of the sheet metal being used. This will provide us an idea about the limit of drawing which is carried out. Okay. So this again further extends to a new parameter known as limiting drawing ratio. Okay, so limiting drawing ratio basically gives the limit of maximum means it is the maximum value of this ratio which gives us a limit of drawability. Okay. So the limiting drawing ratio basically represents maximum diameter of a blank which can be drawn into the shape of a cup with given punch diameter without any failure or rupture. So the next thing is limiting drawing ratio. Limiting drawing ratio. It is also known as LDR. LDR. Okay. And this is defined as the maximum value of this drawability ratio. Okay. So LDR is nothing but dB over dP, the maximum value of this ratio. Okay. And this defines the maximum diameter of the blank that can be drawn into cup shape without failure or rupture. So gives an idea of maximum diameter of the blank that can be drawn into cup drawn into a cup without fracture or failure. Also, this limiting drawing ratio can be represented in terms of the efficiency of this drawing operation, okay, which will contribute to the losses due to friction, that efficiency term. Okay. So basically, this LDR is nothing but e to power eta. This is eta, where eta is the efficiency. This eta is nothing but efficiency. Efficiency that accounts for frictional losses. Accounting for frictional losses. Okay. So this is something called limiting drawing ratio. Also, some factors which affect the drawability include the die radius, the punch radius, etc. Okay, so some of factors affecting the drawability. Drawability are the die radius, and the die radius should be about 10 times the thickness of that sheet which is being used as blank. Yeah, so this is die radius. Should be around 10 times the sheet or blank thickness. Blank thickness. Okay. Next one is the punch radius, because if punch radius means basically the radius of curvature of the contacting portion of punch, which meets with the blank. So if the particular section is very sharp, it may lead to local thinning, etc. Okay, so the next parameter is punch radius. Punch radius should be so that it should be not very low, because it will create a sharp edge and that will lead to thinning. Okay, so sharp radius may lead to thinning and tearing, and we have seen that thinning should be avoided. The next factor is the clearance between the punch and die. It should be there should be some allowance between the punch and die, so the clearance should be around 20 to 40% than the thickness of sheet. Okay, so clearance between die and punch we are talking about die and punch, so we should not consider sheet. I mistakenly told sheet here. There should be some clearance between the die and punch, so that the punch can easily carry the sheet into die cavity. So there should be some clearance for easy movement of the punch. Okay. Die and punch should be 20 to 40% higher than sheet thickness. Okay. Also, to avoid friction, there should be lubrication. So friction is also a factor. So lubrication, we should say directly. Lubrication to reduce friction. Okay, so these are some important factors that influence the drawability of any sheet metal. Okay. So we will close for this class now. We'll see some more parameters related to drawing in the next class. Thank you.